Well, hello. My name is Bashar Kabalan. You can call me Bash. Tell you a bit of myself. Just given that this is actually the first YouTube video I ever upload of recording myself, which is going to be quite an interesting experience, and also please do I guess forgive any newbie errors or mistakes doing these things. It's going to be my first, and while I was preparing with this, I was just worrying a lot about so many things. But then I thought, if I keep doing that, I'm not going to get anything out there. So I'm just going to improvise it, just do it the way it is. Obviously, there are going to be a lot of things to work on and progress, but I wanted to get something out there that I can actually start building on. So, to tell you a little bit about myself, I'm a crowd planning consultant. I have a PhD in crowd modeling with a background in civil engineering, and ever since I finished my PhD, I was always started doing a bit of things with Python, and then one thing led to another, and then I found out about data science and scikit-learn and machine learning and artificial intelligence, and I started getting really, really fascinated by all these things and how a few lines of code you can do some really powerful models and algorithms. So ever since 2016, I've been trying to get into that world, get some experience, upskill. But as you know, juggling that with workload, changing countries. I moved from Paris to London, so that by itself was taking a lot of energy and time, relationships, family, all type of things. It wasn't really easy to learn some of these concepts. And especially, I think I would say one of the biggest mistakes I've done is to depend a lot or invest a lot in online learning, which I think is very useful, but never gets, well, in my experience at least, never really gets your hands dirty into building stuff and actually doing the learning that really sticks in your mind, and helps you learn all different tools that are used in the industry that are quite powerful. Another mistake I've done is trying to do everything over the weekend, in my room, coding and doing online courses. Over the past 4 years, that really didn't work. And then I started going, first of all, getting myself out of my room, so going to the British Library, which increased my productivity a lot, but also going to a lot of events in the AI coding world. And in one of the events, I met Bezard, or you can call him Bez, from Founders and Coders, who introduced their deep learning bootcamp, which has 8 weeks intensive training, and then it spans off around 18 months with ongoing learning. So I joined the Machine Learning Institute at Founders and Coders, and I started the course in end of October, and I'm extremely excited about it. It's really a great course, and throughout this course we're going to learn how to build end-to-end deep learning modules and how to fine-tune large language models. So it's really amazing experience. The past 4 weeks have been, I really think I learned the past 4 weeks more than I've done in the past 4 or 5 years, honestly. The environment, the pressure they put us onto, the teamwork, the conversations, the intensive focus. It's intensive, it's full time. So we're spending 5 days a week building some of the most advanced and state of the art architecture. So I'm learning a lot of things. So I'm going to start this the series of videos where every week I think I'm 4 weeks behind. So what you're seeing here, we've already done it about 3 weeks ago or 4 weeks ago. But I thought, better late than never. So every week I'm going to try and upload a video and explain some of the things and the concepts we learn. So I'll start this. I'm going to call this series "Becoming a Machine Learning Engineer." And in week one, we learned about some of the main concepts and ideas behind natural language processing systems. So in week one, the objectives were, again, like I just mentioned, understanding some of the main concepts of NLPs, familiarize ourselves with the most prominent architectures and techniques, and actually deploy an end-to-end language detection model. So basically, we'll build an app where you can send it a text in one of five, I think, or seven different languages, and the model has to detect which language is it and give you back the result. Excuse me. So the way the week was structured, as you can see here, oops, we code basically on Monday. The challenge is introduced. So basically, what I just explained to you, and then on Monday and Tuesday, we start coding. First of all, we go and try to understand the concepts. We read a lot of resources. We talk amongst each other. We make sure we've understood what we need to do. So usually that's done on Monday, and then Tuesday we start the coding, start getting our hands dirty with the code. Wednesday is reserved for research. So Bez gives us a number of research papers, some of the most recent research articles out there. Each team reads them, and then at the end of the day, we present what we understood from these results. And most of the time, we actually use some of them during the week in our coding practices. Thursday we focus again on coding. Friday as well, and Friday where we gets really start feeling the stress and the pressure because we have a presentation in the afternoon, and Bez goes on the server, and he clicks sends a request and sees what each team managed to do. So it's usually a stressful day, but also very rewarding if the request successfully gave back some good results, which is most of the times the case, but sometimes might not be the case. So the first challenge, I'm not going to dwell a lot on that. So as I've explained, we have these 7 languages. The app will send a request, or basically the app will receive a request with a phrase or from one of these languages, and it has to give back an estimation or probability estimation of what language that is. So it will give back 7 numbers representing probabilities, and the highest probability usually basically is the language that the model is most confident about. During that week, we learned about Word2Vec, and we've used Pytorch, Python, Jupyter notebooks, and also FastAPI to actually build the app. But most of the code happened in Pytorch, switching and Jupyter notebook for developing and testing, and then once we're ready, we've put everything in Python for basically production mode. So that's the main article. That was, I guess, the article that was allocated to our group. It's the Word2Vec article. So it introduces the Word2Vec concept, and basically introduces the main concept of word embeddings, which I would say was the main idea of this week, is really understanding the word embeddings and basically how do NLPs, or natural language processing system, take some text and transform it into a bunch of numbers that could represent syntax or semantic meanings to the model. The model doesn't understand words; they understand numbers and bits and bytes. So it's how do we transform a sentence or a text into a matrix of numbers that the model can use to train and to fine tune and to find some semantic and syntactic meanings in that. So yeah, super, really, really cool, very interesting read. Um, and in the paper they demonstrated how obviously these word embeddings, how they are capable of capturing these syntactic and semantic relationships, and what they were focusing on is doing that with less computational resources. So the goals of the paper was develop this new architecture, and they were seeking, what they want to do is preserve that linear regularity among words. So, for example, if what they were trying to achieve. So, if you use like the word king, you would represent it, with a vector of numbers, and then you use the word man, represented with another vector of numbers. And what they wanted to actually achieve is that if you subtract king, or the vector representing king, from the vector representing man, oh sorry, I think there's a small mistake here. If you subtract vector king plus vector man from vector woman, they'd like to expect that the result would be the closest to vector queen. So king is, the analogy, king is to man as queen is to woman. So they wanted to really preserve this linear relationship. And so they developed also or designed new comprehensive test sets to measuring both the syntactic and the semantic regularities in that model. So previous, they did a bit of work, or a bibliography, I suppose, of previous work. So they looked at Where's the complexity coming from in large language models? And usually it's in the nonlinear hidden layers in the model. And they wanted actually to explore some simpler models that may be able to represent the data the way I just presented in the earlier slide. So it might be simpler, but actually that could allow it to be trained on much more data efficiently. So when it gets complex, it seems, when the models or architecture get complex, it becomes really inefficient to train them on a large amount of data. But the more you simplify your model, the more you'll be able to do that. So the model that they did, previously, so I suppose they were successfully trained in two steps. First, you look at the continuous Word vectors. They are learned from simple models, and then the n-grams and n-elms are trained on top of these distributed representation of words. And so in this word, they introduced two concepts, the CBOW and skipgram. And basically, if you remember what I just said earlier, which is they had two parts to their model. The first one was the linear part, where they creating all these word embeddings and they're learning how to represent the semantic and the syntactic representation of words. So that's the linear part, and that's where CBOW and skipgram comes in. So CBOW and skipgram, their objective is to train the model to create these word embeddings, to create these vector representation of each word, and then they take that and they feed it into a feed-forward neural network large model, or a nonlinear model, where they add nonlinearity. I think they add a ReLU layer, where basically they create the ReLU's objective is to identify or capture these complex nonlinear relationship between different words. So yeah, so focusing now on CBOW, mainly because that's the one that I used later in the model or in the project that we did. In CBOW, what happens is the following: the word gets tokenized, so there is a choice of the number of vocabs you want to have in your list. So let's say you have a corpus of 1 million words. You can actually choose that you want to represent 15,000 of them, because you think, because this is a hyperparameter that you can tune. But basically what you're doing there, you're making the assumption that 17,000 words or vocabs are enough to represent your corpus, because there's a lot of other words that are not repeated enough, or for many other reasons. So once you've chosen the vocab list, each word now will have a vector representation. So you receive a sequence of words, a sentence, and then basically you will grab a word, or each word of this sentence in CBOW. You will grab each word of this sentence, and then you will take words before it and words after it. And you will use these words to try and predict your target word, right? So let me rephrase that maybe to clarify a bit more. Let's say we have a sentence: the boy went to school. Okay, so you grab the word boy. Okay, so that's your target word. That's WT basically on this diagram. And then you grab the and to school, and these are your context words, which you can see here as WT minus 2, WT minus 1, etc. And you try to use the context words, to predict your target word, WT. And basically what you do there is you take all these context words, you grab their vector representation, you sum it up, and then you do some operations, and you predict the word. In skipgram, it's the other way around. You take a word and you try to predict the context words around it. So I guess the next slide, maybe. So as I mentioned, my focus will be on CBOW, because that's the one I used. So as I said earlier, you make this assumption and you get your word embeddings matrix initially, which starts with just initial numbers, right? Between 0 and 1, it's just random. And it will have as many rows as words as you have in your vocab list. So if you made an assumption that you just want 16,000 words that represent your entire corpus, then the word embeddings will have 16,000 rows, each row representing a word. And then you make another choice of how many dimensions or features you want to use to represent each word. So you might choose that each word will have one feature, which is not great, or it might have 16, 32, 512. It's a choice you make again, and that's something you might fine tune later or tune later on during hypermetric tuning. But basically, that gives you your initial word embedding. And then what I mentioned earlier, you take, let's say, a word, that's your target. Again, in our example, it was boy. You take the words around it. So if we're assuming a window size of 2, that means we grab 2 words before and 2 words after. In this case, because boy has only 1 word before, we'll take only the and 2 words after to school. And then for each of these words, we'll go to the word embedding and we'll go search for them in these rows and grab the row that corresponds to them. So now we'll end up with 3 vectors. 3 vectors. Each vector represents a word, and each has the number of dimensions n that we've already chosen. We squish all these words together to get only one vector. There's a choice there again between adding them up or averaging. And then these go into a fully connected linear layer and outputs a probability. So it again outputs a probability of what word the model predicts from these context words that you provided. So again, here we are still linear, as you remember, to preserve that linear relationship between the word that the article aimed for. So we haven't added any non-linearity yet. And then, they showed some of the results, but the main thing that struck me is, during the course, we were struggling with, accuracy and training accuracy, and is our model good, and why is it not presenting? And then you can see that, we were using, I think, dimensionality, which is the number of features that was represented in by the value or the variable n in the previous slide. We were looking at like 50 or even less, actually. I think I started with like 16. And then our corpus was, I believe, I don't know, maybe a few million words that we were training on. And then I saw the results from the article, and they tested up to 600 dimensions and on a corpus that is up to 780 million just to get to like 50% accuracy. So the accuracy on subset of the semantic syntactic. So that just put things in perspective and made me focus on learning the concepts and not focus too much during that week on getting that training accuracy, because I think we're a bit far from there given the tools and the data sets we were working with. Cool. Okay, well that brings us to our model. I was working with 3 team members, and the first thing we did is made sure we understand the conceptual model behind it. So we had 2 parts in our or 2 main work streams, I would say. Writing the code or the concept of the training process and the inference process. And what we understood, what we learned is that we will receive our data. The first thing is to do is to train or to tokenize our data. Tokenizing means taking a bunch of words and representing them into numbers that represent indices. So let's say I have the boy went to school. The will be represented by the integer 0, boy 1, 2, 2, 2, school 3. So that means tokenizing. So now each word has an index that represents it. And then obviously you can grab the word from the index as well. So it works both ways. Then once you've done the tokenizer, we do the CBOW model. It gets trained, and that matrix that you saw earlier, the word embedding, that's what gets trained, and that's what's the output of the CBOW model once the training is done. So once the training is done, now we have our embedding weights. So the vector that represent each word in our corpus or in our vocab list, and now we can use it to train the language model. So as you remember, the CBOW model is just linear. We haven't introduced any nonlinearity to capture any complex relationship between words. But in the language model, we take the embedding weights from the CBOW model, the output of the CBOW model, and we use it as input to our language model. And then in our language model, we add a nonlinear or feed-forward nonlinear model using the ReLU activation. And then that's what we use to train on detecting basically the language. So now our language model Once it's trained and its parameters, the model parameters are tuned after the training process, it again we get all these parameters out, the tuned parameters, and we use that in the inference process. And what means is that now our model, or one version of our model, or our trained model, if you want to call it, with the updated parameters, is capable of receiving an input sentence, processing that, and then outputting probabilities. And it's a classification task and gives us a probabilities for each of the seven languages that we saw earlier. So the model will tell us, I think, 40% of what you the sentence that you give me, the model will say, I believe I'm 70% sure it's English. I think still 20% might be French, 10% might be Turkish, and maybe zero the others. So that's basically the output that you would expect, and that would happen in the inference process. So there's no more training, there's no more looping. It's just one pass into our model, and we output the probabilities and the results. So let's maybe dig a little bit into the code. As you can see here, this is the CBOW train. So the first step, as I mentioned, of this work is to actually get the word embeddings. So training our model to create vector representations of each word in our vocab list. So as you see, we first created the data set, we tokenize it. So now our data set, the entire corpus, which we had, I think, corpus of all seven languages, we all mishmashed them all together and used the tokenizer to represent vocab, each vocab by an index, so a token. Then once we've done that, we've defined our model. So as you can see here, we have the CBOW model, and if we look in the model.cbow, which you see right over here, you will see it's just a linear model with an embedding layer and a linear layer, a fully connected linear layer. That's all. We defined our function loss, our optimizer, to calculate the gradients and to modify the parameters, and then finally the loss function to evaluate if the loss function is decreasing. That means we are getting towards our target, basically. The loss function is basically like the difference between where you are now and where you want to get to. So you want that loss function to be decreasing all the time. And then we train the model. So as you can see, this is one iteration. So here we're training over three epochs. And then we go through our data set one by one. We have the context and the target. So the target for CBOW, the target is the word we're trying to predict, and the context are the words around it. We go through optimizer, we get our probabilities, we calculate our loss function, we update everything, and then we keep iterating until we decide to stop the model. Once we've done that, we save the model that we're happy with, that we are going to use later on in the language model. So basically what you see here at the end, the CBOW epoch.pt file, that's going to contain the word embeddings that we are going to use in the large language model, which is you can see here. So that's our the language training model. So as you can see, the first thing we do is we load the learned embeddings that we learned from CBOW. Then again, we define our language model. This time, if you see here in the model.language, if we go in there, you will see a nonlinear layer, which is the ReLU activation. And then again, same thing as before, loss function, optimizer, define how many epochs we train, and then finally, we save now the model that we are going to use in our application, in our app, that is going to receive a sentence and predict what language it is. And I just wanted to say one last thing here. Is the tokenizer is quite important, because it will provide the vocab list that will define our word embedding layer. And then that's the FastAPI code. So this is the main code. Well, this is the code basically that will go grab the vocab list, because it's quite important. It will go grab the learned embeddings from the CBOW model, and it will also go grab the trained language model, so the .pt file. And then once it has all of these, it will use these, and basically, we run the app on the server. It will wait and keep hearing, and then we will do a curl request, send it a text, a phrase, and then it will come back with a result with the probabilities for each of these languages that you can see here. So it will provide us with a probability for German, Esperanto, French, Italian, Spanish, Turkish, and English. So this is what you can see here. So we've launched the app using the UVcorn command, and you can see here I gave it a question, or basically I wrote something in English, and it predicted a bit over 50% Turkish and about a bit over 40% English. So not too bad, but not right, to be fair. But again, we had 5 days. We had a limited time, as well the resources we had in terms of data set, computation power, wasn't enough. We probably trained for less than an hour. But the point, the whole point of this was to learn the concepts and not necessarily focus too much on the results. Yes, and I think that is it. It was really a very challenging week. I think that week the main challenge was actually all the software developy stuff, if I can say. So setting up the server, your GitHub account, SSHing into the server, training on the server, moving files between your local machines. So all of these were new to us, and as a lot of us in the bootcamp, don't have this background. It that took a lot of time, to be fair. But then I think the main objective here is was achieved. We had a really good understanding of the concept of word embeddings, how you present words into numbers, and how do large language models use that to extract complex relationship between words and do whatever task you are giving it. And also, it was our first end-to-end experience. So we wrote the code, we understood all the concepts, we wrote the code, we trained it, we extracted everything, but then also we built an app, the Fast API, that could connect to a server, receive requests, and send back responses. So we started with the end-to-end experience, which I think we were also successful with. And we started also getting used to reading research papers, understanding them, and actually start to apply them. Because this week we read the Word2Vec article, we understood the CBOW, and actually we went and implemented it, which was quite cool. So yeah, really really happy of the first week, and I got really the feeling of what it is and how exciting and high pressure and stimulating and motivating it is. And going through the difficulties, and at sometimes you feel a bit of anxiety, am I going to, and actually managing to finish it gave us a lot of confidence and excitement about the upcoming weeks. So yeah, super happy, super excited about the first week. And next week we are going to do a search engine project. So in the search engine project, we will receive, basically, we'll receive a query, and we need to basically suggest the 10 most relevant resources for that query. And for that, I believe we are going to implement the two tower model architecture, or the two tower architecture. So yeah, super excited about that, and hopefully I'll create a video on that next week as well. Thank you very much, and yeah, it's pretty cool. This is my first YouTube video. I'll just finish recording now and upload it in a bit, and yeah, I guess that'll be the first intro to content creation. So very excited about this. Watch the space, and hopefully more exciting things and higher quality videos will start arriving progressively. Thanks a lot. Bye bye.